All right. Sorry for the delay. Had a little bit of a stream snafu, but we'll go ahead and get started. Um, Today we have a special guest with us, Mercury Silver. They are the creator of the Sonic Physics Guide, and they're here today to show us their their like concept for making a new or for improving sonic physics. And it should be a lot of fun. It'll be very technical. So there are a couple of things I wanted to go over first, and that is that you really need an understanding of the sonic physics guide to get the most out of this. And to do that, I've put together a video, actually on my other channel, GameFAQ Special, which gives a brief overview of how classic Sonic physics work. So I encourage you, if you're looking to get the most out of this, and you're kind of new to this, to the idea of creating Sonic physics from scratch, watch this video. Then go to Mercury's guide, the Sonic Physics Guide. It has been worked on by many other people, of course, over the years, but the original guide comes from Mercury, and again, they're going to show us today how to improve essentially an improved implementation of this guide. So with that introduction, I will give it to Mercury. Welcome.
Hello, everybody. Thanks for having me overbound. I'm excited to talk about sonic physics today.
Cool.
So, like the Sonic's Physics Guide.
Yeah, I'm gonna share your screen here. One second.
Back in
Yeah, just give
muggy
me.
prehistory when I first made it.
Yes, go
Like,
ahead.
fan game physics were in a right state, they were not guaranteed to be very accurate to the classic games. But nowadays, I mean, Sonic fan games are fine, right? I mean, anything that you look into, whether it's Fallen Star, Sonic Hoshi, Sonic Galactic, they're all going to play great, right? So, like, what's even the point of all this? The Sonic Physics Guide exists. Um, all the people who have worked on it after me picked up the torch. Shout out to Lapper, who has done just a disgusting amount of effort on it, adding all the GIFs and explanations and illustrations.
Yes,
Like, it's, I don't want to say trivial, but it's pretty obvious how to make an accurate Sonic engine today. But
absolutely.
I have always been interested in like how to go beyond what the classic Sonic physics do without breaking them. There's a handful of things that bother me about how the original games work. In the physics guide, there are these helpful illustrations of problems with the original physics engine, like how he behaves weird on angled slopes and um, how he changes mode erratically. And we've probably all, if I can show this quick video of Starlight Zone here, we've all encountered things like that where Sonic is supposed to stay on the ground, but for whatever reason he just doesn't.
Sure.
And the original developers even sort of acknowledged this in the instruction manual to Sonic 3. Sort of infamously, they talk about Dr. Robotnik's diabolical traps that take advantage of Sonic's ultra fast speed. If you fall into the wrong trap, you might have to reset the game. So, like,
I was
they knew that
always
moving.
looking for those, but I never actually understood that we're talking about the broken physics.
Now, to their credit, like, I have put thousands of hours into the classic Sonic games, and you get stuck in the terrain and have to reset, like, maybe once in a blue moon.
Yeah.
Um, but after working on Time Twisted with you, I've bounced around between a bunch of different projects. Like I was working on Sonic 2 HD for a while, and I've been attached to Lapper's Sonic Studio project
Hmm.
off and on, giving advice. And so,
You also
like,
worked
with
on Triple Trouble, didn't you?
yeah, that was mostly um,
Special stages.
giving input on the special stage engine and a handful of things.
Okay.
But the core physics, I didn't touch.
Outside of
So,
everything you already described. Go
like in
ahead.
the case of Sonic 2 HD, everything is 4 times bigger. So you can't like use the original engine.
Hmm.
All of the data for the zones is pixel based. So once it's 4 times larger, you can't use the same pixels.
Right.
And I've also had ambitions to make like a game engine that people can use to make games other than Sonic or make their own decisions about how big the characters should be or how fast they should move and stuff. So if you adhere very precisely to the way the original games worked, you're going to wind up with a lot of issues that didn't occur in the original games because they were bespoke. They were designed specifically around those issues. But when you're like, hey, you want to make a platformer, then it would make sense to do things in a way that has more flexibility.
Yeah.
Like you want platforms to rotate, you want the gravity to be not just flipped up and down like in Death Egg Zone, but maybe left and right. Like all these kinds of advantages that you don't have if you are using 100% accurate original physics. And also, the original physics are tile-based, which means there's a lot of data in the environment, tiny little tiles with special flags all over that just put a huge burden on level designers. They can't just like easily sketch out a level. They have to decide, oh, this is top collision only, and this is left, right, bottom collision. This block is associated with this uh, tile shape and stuff, and it's just a lot of rigmarole. So I have been sort of obsessed with the concept of both simplifying the way the physics are implemented and improving them, sort of solve all those problems together. I think it was Shigeru Miyamoto who said like a good idea is something that solves multiple problems at once. So, like, can I make it easier to work with, easier to program, and also solve some of the issues I have with Sonic Collision? So, I want to cover some of the more abstract basics of Collision because I don't know where anyone in the audience may be coming from. Like some people may have programmed a fan game before, some people might be getting into it for the first time. And because I'm not going to be talking about strictly how the original games work with info that's going to be explained in the physics guide, I will probably be referring to some concepts and some terminology that aren't covered there. So I just thought I'd do like a quick timer um,
Sure.
on some of the basics. So first thing is that video games aren't real. That's a knowledge bomb for you. But
Wow.
so everything isn't made out of molecules. If you want to bump into things, you have to simulate it. And these simulations happen step by step. So like here's what I'm going to call an actor. And you can think of this as like the player character or an enemy, anything that's going to bump into the terrain, the environment in the game. So I have chosen orange, as you can see on the legend here, for actors, and blue for terrain, because I have been advised that they're very colorblind friendly colors, so hopefully they're easily distinguishable. So in a game, the player character, when they move, they don't occupy the intervening space. They just sort of appear from one step to the next in a new location, and the game has to decide what happened in between.
So
if
that's
we
like
put ourselves,
you're just talking about like a typical game loop of like having a player and it moves and yeah, okay.
yeah, it's like sampling a data set on a graph or something. Like you have the points at which you have your data, and in between you don't have anything. Like
Right,
the game doesn't.
because of the speed. You apply
Yeah,
speed all at once. Okay.
and it can be a variable frame rate. So I'm not saying specifically it happens this many times a second, but from one tick of the simulation to the next, the speed has been added to the position of the actor, and so now they're in a new location.
Yeah, that would be like physics steps, more or less.
Yes.
In
And in like, if you just imagine some game like Asteroids where you don't have terrain, you just are, well, I guess you're always in the center of the screen in Asteroids, but basically like a space shooter where there isn't terrain, you just fly around freely. There's nothing to bump into except for other enemies and stuff.
sure.
That's probably a good point to make, is that I'm going to be talking about terrain collision because that's most relevant to Sonic. Um, Enemy and pickup collision, like touching a ring or a badnik or something, those aren't really physical collisions in the sense that they don't adjust the player's position to smoothly move along surfaces or stay outside of things. They're just simple overlap tests, like, oh, you're touching the ring and the ring disappears. You're touching the enemy and then you're put into the knockback state. So
Yes,
we're
it's
going to
not
be
as
covering just,
important if they're accurate or not.
right, they usually don't move the player because the enemy or the pickup will disappear as a result of the collision rather than the positions being adjusted to make it look like you've bumped into them. So the simplest game with collision that I can imagine is like some kind of really simple endless runner where you just have a floor and it's just infinitely wide. It's just the floor. Like it could be defined entirely with a single y coordinate. Like this is the height of where the floor is. And you've got your character and they stand on the floor and the character jumps and you want the character to land. Now, the way to do that would be to say if the player is too low on the screen, depending on the engine, y coordinate can be negative or positive, so it's kind of hard to talk about it in a general sense, but like um, I will assume that the y direction is positive so that your y coordinate increases as you fall, since that's what I'm used to.
Yeah, that's
So
math. So
you can say if the bottom of the player, which has a known y coordinate, it will be the player's center, for example, in the case of this box, and then this height here. And for the discussion today, I will be referring to this horizontal distance here from the middle of the player to their right edge or their left edge, because it's the same distance because they're symmetrical, as the x radius, and the vertical is the y radius. Now, broadly speaking, if you have a circle, the radius is the same all the way around, so there's just a single value that you would call the radius.
hmm
But if I'm talking about a rectangle, its width and height can be different. And so just for consistency with talking about circles, it's easy to say, oh, it's the radius. So if I mention the radius, I'm probably talking about the y radius because that's involved with the height of the player and is therefore determined involved in how high off the ground they are and stuff like that. So um, just so that you understand the terminology I'll be using. So if you have a player of some kind, you know the bottom edge of the player, it's their y position plus their y radius. So you can say if that value is greater than the y position of your infinitely defined floor, then the player should be set to the position of the floor minus the player's radius. So from one step to the next, let's say the player's falling, And they could be falling really fast, which is good for demonstration purposes. So like in one frame, they're above the floor. Then the next frame, they're below the floor.
Mm-hmm.
Well, in this frame, if you ask, is the player's bottom edge below the level of the floor? The answer would be yes. So you would say set the player to the level of the floor minus their y radius, and now they're on the floor. And so no matter how fast they fall, and no matter where they start, where they end up, at any time, if they are below that level, then they are able to be moved to the level of the floor before the graphics are redrawn, and so it will look like the character has hit the floor and can't go through it. The floor is solid. That's terrain collision in pretty much the simplest possible case.
Sure.
And a lot of that might seem obvious, but the reason why I'm starting from the simplest possible case is because now we can move on to a more complex situation. Like, what if you have multiple objects that you want the player to collide with, like jumping on them, or let's say you have a wall of some kind and you want the player to hit it. Now, instead of being able to ask if they are below a certain point, you're going to have to check all these other rectangular boxes to see if they're touching them.
Mm-hmm.
Now, this rapidly gets very complex, but it's
Yes.
also been done to death a million times by a million games. So there's tons of resources out there. To see if two boxes overlap is a really simple algorithm. You're basically just comparing their sides to see if the right side of the player is greater than the left side of the box, and basically the same principle applies for all four sides. And you can say, yes, I am overlapping the solid block of terrain. The actor is overlapping it. But now that you have more than just one floor, you have to make a decision about which direction to move the player, because remember, the player is moving in steps. So from one step to another, they're just in a new location. And when they're in that new location, if they're touching something solid, you don't want them to be overlapping the solid. You want them to be on it or next to it somehow. So what is the algorithm for determining where they should go? Now, if we were falling really fast, like in the first example, and so the player in one moment, here I can copy it so that they're both on the screen at the same time, player in one moment is up here above a
Mm-hmm.
floor piece, and in the next moment the player is down here. Well, you will have never overlapped. The player will have never overlapped this floor piece. So the player will never collide with it. In reality, the player would have occupied all the space in between. But because it's a stepwise simulation, the player basically transports through it. And this is a really well-known problem in collision. It has a name. I've heard it called tunneling.
Yep. Yeah, I've heard that
And
term too.
it's fairly well popularized. It's not a hard thing to solve. Usually, the way it is solved is by just increasing the resolution of the simulation, saying don't allow the player to fall faster than the size of a box so that they will occupy more of the space in between. They'll never occupy all of it because video games are fake, but they will occupy enough different locations that at least one of them will overlap. And you can say, oh, the player's landed on the floor. We're good.
Yeah,
However,
another term for that is substepping. If you're using like
yes,
rays, continue. Yeah.
exactly. So it's not just a matter of traveling all the way through the floor, though, because, and I can demonstrate this better with a bigger box and player. let's say the player appears here and their midpoint is above the midpoint of the box. So you can say,
Below,
you
but
can
yes.
use that as like a tiebreaker to say they should be moved up out of the box.
Well, their midpoint
Or
was below, but I think I get what you're saying, right?
like well, let me
Or are you talking
draw.
about the player's midpoint or the box's midpoint?
Yeah, if the box has a midpoint,
Ah, okay. I thought you were talking about the
then
players.
if the player's center is above the midpoint, you can use that to say the player should be above the box.
Yeah.
So it's not just a matter of the player tunneling all the way through. If the player moved from one step to the other and they were suddenly here, they would know that they hit the box, but they would be saying, oh, my center is below the midpoint of the box, so I should be moved out in this direction.
Mm-hmm.
Which is why there's all kinds of different algorithms for deciding which direction the player should be moved out of an overlapping solid. And one can be like, oh, well, what direction were they moving in? If they were moving down, they should be pushed out in the opposite direction of their movement, and that would prevent them from tunneling because any downward movement would be counteracted by always moving up. But it does require substepping of some kind, assuming, I mean, it all depends on the kind of game you're making, because if your player moves very slowly, like it's an RPG or something, they're never going to tunnel through anything. But if it's a Sonic game or something where you're moving very quickly, then you can pass right through stuff.
Sure.
However, there's a much more irritating problem that isn't as celebrated as tunneling that I want to mention, which is, let's imagine you have two pieces of ground here, and they are touching each other,
Mm-hmm.
and you have player, and the player is walking along the ground. They have no problem because they never overlap anything. They just move, and it doesn't matter. But if the player were falling, at some point, the player could be overlapping both of these solids.
Right.
And so, which direction should the player be moved? Well, let's say, just for the sake of argument, the player was here. They're falling down at like this vector. They moved from here to here.
Mm-hmm.
Well, they're both moving right and down at the same time. And now they're overlapping two of these solids. What we would want is for the player to land on it as ground that was flat. But the problem is that as you test for collision with solids, they have to be checked in some order. They don't get to be checked all at once.
Right.
So you're going to be looking at either this one or this one first. And if you're looking at this one on the right first, then the player is moving right and they're moving down. So how do we decide whether the player should be moved to the top or whether they hit it as a wall and hit it like this and slide down instead of landing on it as ground? Now, if this were just freely floating in space, it wouldn't matter. You'd probably pick one based on the player's position, and they would either land on it or they would hit it and they would slide down, and it wouldn't matter. But if you've got ground put together like this, and the player hits this right piece as a wall, then you're going to feel getting stuck. You're going to as the player, if you're falling down, you're going to hit the seam here, and you're going to lose your speed, and it's going to feel like you hit some kind of snag or a trip up.
Mm-hmm.
When in reality, you just want this to be flat, right? The fact that there is a border here is not important. It's just an artifact of the fact that you're making things out of boxes, and boxes that are adjacent have these corners, and they're going to get in the way. And the same thing is going to happen if you have a wall with a cap on it. The player could be moving and they could land on this piece right here as a floor and lose their downward speed. So if you were jumping toward this and you hit it as a wall, you're going to feel yourself stop and snag on it and fall down. Now, this kind of thing actually happens in games, old tile-based games, because every tile is basically its own box. And so you can see speedrunners taking advantage of this if they hit things just ever so precisely. And like the original Super Mario Brothers or Super Mario Brothers 2, they can like Mario should only be able to jump in those old NES games when he's on the ground. There's no wall jumping in those games. But if they do it just frame perfectly, they can jump off of a wall, sort of simulating a wall jump in a game that doesn't have one because the game actually thinks Mario landed on the ground. Whereas, you know, ideally, this would just be a wall and this wouldn't be here and you wouldn't have that problem. So this is also not necessarily a hard problem to solve. You can do it in a couple of different ways. One of which is separating your collision checking into separate axes. Instead of moving, like let's say the player has speed in a vector that's like they're moving down and to the right,
Mm-hmm.
um, like this. So instead of moving the player from position 1 and then adding x speed and y speed at the same time and then checking to see what they overlap, you add only one component of the player's speed at a time. So, for example, in this case, their x speed would be a vector like that, and their y speed would be a vector like that. So if you only add the x speed, then the player is going to,
Yeah,
for
yeah.
example, start here and then wind up here. And so you
You're
say, well, if they
speaking
hit
of the.
anything, they
Sorry.
definitely hit it as a wall because they were only moving horizontally. And then you do, sorry, did I talk over you? I didn't catch that.
I was just going to say, and you're talking about that's how Sonic the Sonic Physics Guide outlines it, and how the Genesis games work is moving discretely in the X and Y in separate
Well, the Sonic games actually use a convoluted hybrid, so it's kind of hard to talk about them in generalities. But if you were just making a simple game about boxes, which is sort of our abstract discussion as we build up to Sonic from here,
Okay.
you could easily solve the did I hit it as a wall or did I hit it as a floor problem by just separating your movement into two separate uh, steps where you move horizontally, check to see if you hit any walls, and then if you did, you have a new position. And then if you do the vertical movement, well, you're not going to hit any floors until you actually hit a floor because you've been moved out of all of the walls. And that's one way of solving it. Another way of solving it is something that Sonic does, which is to not have the character be a perfect rectangle that tests for overlap, but by being a collection, sort of a bristly collection of sensors. They've got like a right wall sensor and a left wall sensor and a ceiling sensor and two floor sensors. This isn't necessarily to scale for Sonic, but it's close
Close
enough.
enough. Yeah.
So this box here is just for demonstration purposes, but if it weren't there, you can think of the Sonic object as just being a collection of these straight lines, essentially. And it's
Mm-hmm.
going to be a lot easier to demonstrate this with moving the terrain relative to Sonic rather than moving Sonic relative to the terrain, because my little app here doesn't let me link these objects together. So I'm just
Okay.
going to move the terrain against the sensors. So if you see that he is overlapping a piece of terrain, the box might be be a good way to do that. Anyway, yes, here's a good example. The rectangle, the orange actor rectangle here, is overlapping both of these
Right.
solids. But the horizontal sensor, because it's infinitely thin in the y-axis, it's just a line, can only ever be touching one of them. And so it's going to say, hey, I'm hitting a wall. I'm not actually hitting a floor here because these sensors aren't touching it.
Do you remember what that function is called in Game Maker? There's like a line draw function for collisions, isn't there? Maybe it's just
Uh, I have been using my own collision routines in Game Maker so long, I do not remember
I
what
could
it's
be
built in for.
remembering wrong too because I haven't used Game Maker in a while too, at least not extensively. Anyway, but it's a raycast in a lot of engines. At least that's one way to implement it.
Yes, the original Sonic engines don't have modern processors with all the floating point operations, and so they're not going to waste time doing all the fancy math if they don't need to. And since they're only ever checking perfectly aligned with X and Y axes, they aren't using angles in between. As you can see, all these sensors are either straight left and right or straight up and down.
That's fair. Okay, I'm getting ahead of myself.
Yeah, they do the equivalent of a raycast. It's just simplified.
Yep.
Um, this doesn't completely solve the problem because if you were moving fast enough, like one of the floor sensors could be touching and then you would have the same problem. But by separating it out and substepping and all that stuff, you can solve those problems. And you can also say, like, well, separate horizontal and vertical movement is something the Sonic games do to a certain degree. Again, like I said, it's slightly complicated because it's true in some instances and not in others. Um, but this is a lot of sensors, kind of complicated. There's these weird problems that occur when you have multiple sensors, as the physics guide helpfully shows us here. How can I, whatever, bad gateway.
Mhm.
I don't know if I can make it bigger here comfortably for the stream.
I think it's I could see it, and it's bigger on
But because
stream.
Sonic is split into these sensors, it's almost like he's walking on these two stilts, and it's very similar to what I was saying about tunneling, where the space in between is never occupied. So you would expect him to walk up and be able to stand on the tip of this slope, but he can't. One sensor finds nothing, while the other sensor is still on the slope, and it sort of makes this sawtooth pattern as he walks up it, as you can see in this GIF. And ideally, that would not happen. And it wouldn't
Right.
happen if you had a single sensor in the center, or if you had some way of making a wide sensor that somehow occupied the whole space, but they don't do that in the original. He's made out of these thin lines, and that is what they do. So this whole time we've been talking about a discrete solution for collision checking, where the player is moved and then a test is done to see if they're overlapping anything. And this is called discrete collision. Now, if you've never heard the term before, you can think of it as like the opposite of concrete. It's not stuck together. It's separate things. Spelled different from discrete, like discretely reading a comic in class. Not the same concept. It just means separate, basically. And in mathematics, the dichotomy between discrete and continuous, they're sort of opposites of each other. So now I want to move on and talk about continuous collision. And
This is
this
where it gets
is,
exciting.
yes, this is a concept where the actor can, in a sense, occupy the entire space in between. They don't just suddenly originate in a new position and tunnel through stuff. Now, Sonic has, I actually had to go back and look at the physics guide to refresh my memory on this because it is slightly convoluted, but Sonic actually uses a sort of hybrid between continuous and discrete collision,
Mm-hmm.
where if Sonic is on a slope and there's some kind of wall or whatever, as he moves, the game says, how do we tell if he's hitting into the wall? So they use his wall sensor, which is going to be this horizontal one,
Mm-hmm.
and they're essentially measuring the distance from his center to the wall.
Right.
And because there's tiles, the game is made out of tiles, it can always tell what tile is at any pixel on the screen, and it can, sort of like a laser rangefinder, look forward and say, hey, there's 10 pixels before you're going to hit a wall here. And in that sense, it's continuous because you know there's nothing between you and the wall because you've basically checked all the tiles up to that point, and they're either empty or they're not. And so you find the earliest wall that you would possibly hit. So you always know, again, like a laser finder, rangefinder, exactly how far away the wall is. So before Sonic moves, the wall sensor says how far away is the wall. And if the wall is closer than how far he wants to move, they don't move him further than the wall. Now, I could say that they reduce his speed by the difference so that when, like, let's say he wants to move, like, again, this is exaggerated for demonstration purposes. Let's say he wants to move that far. Well, the game knows the distance is like that. So it says, okay, you should only move that far.
Yep.
Now, the reason why I don't want to say it reduces his speed is because there's a difference between, this is getting into the weeds, but there's a difference between the speed that you start with, that is the distance that Sonic is supposed to move, and the speed he actually gets moved. It's old programming,
Right.
so it's in registers and stuff. And obviously, once he hits the wall, his speed is set to 0 because he's hit the wall. But it's almost like the speed for a frame is like an impulse value of how far he should move, and so they adjust that impulse value so that he will only move as far as the wall. So that's continuous in the sense that even though Sonic's position does not physically occupy every space in between, because your sensor is like a laser, it knows that there's nothing in between you and the wall, and the equivalent of continuous where he doesn't have to make a decision about, oh no, I went too far, because he hasn't moved yet. He's sort of looking ahead to see how far he can move.
Mm-hmm.
So in that sense, the classic engine is continuous. But they only do that for the wall. Once
Okay.
he's at the new position, they then say, where's the floor? So he finds the wall in a sort of continuous paradigm, but in the other axis where he's trying to adhere to the terrain vertically, and you would want him to be roughly there, it's exactly the same as the old discrete paradigm where he's just updated his position and now says, what the heck is beneath me? Has to do some checks with downward pointing sensors, finds the ground. And that is a little bit of a problem for situations like a slope is indistinguishable from stairs in that sense, because he's here and then he's here. The distance to the floor, let's see if I can do this a little more rigorously. The distance to the floor has increased from one step to the next, but if he's on stairs, the same thing is true, where the distance to the floor has increased from one step to the next. Now you want Sonic to smoothly go down a slope, but you don't want him to teleport downstairs.
Right.
So this is a situation where discrete collision has a little bit of a problem in classic Sonic. It's not a huge problem because the classic Sonic games don't tend to have low steps. So this doesn't really occur in practice, but one
Yeah, I think it's
situation where
32 pixels is the lowest height that you can really have in Sonic.
I think there's some in Labyrinth that are 16.
Yeah, you're right. It is 16. Never mind.
And
And the spring is
the
16 or something like that too, or
yeah,
close
the
to
push
that.
button switches that he stands on and presses down,
Yes.
he can walk off of those. So that's not a very big problem. But a bigger problem is when you have curves where you want to follow the curve and stay on the floor as you go down it. And these are all over the place in the Sonic Advance games, but they really aren't that common in classic Sonic. But there are definitely a handful of locations with shapes like that. Here on the physics guide, there's an example in Launch Base Zone.
Right.
And you can see he behaves kind of erratically when he transfers from the ground mode to the wall mode, because the sensors don't find the right terrain underneath him. He doesn't know what he's standing on in the appropriate way. Like if it was a 360-degree engine, he would be checking beneath him. But here he's just moving horizontally, checking beneath and saying, hey, there's nothing there. Now right here for this GIF, he's not moving very fast. So he is able to acquire the wall and go around it just fine. But like in the video I showed of Starlight Zone earlier, if he moves fast enough, he can be like here, and then here,
And the
and well
ray is
now,
just got, and the ray just, neither the rays just touch anything, and it's over.
yeah, now the sensor is like, I'm not finding anything. But if he was moving slowly enough, then maybe he would have been here, the sensor would find something, and he would go over the floor just fine. This isn't always a matter of speed, because it can also just be your alignment on the ground. Like if you go from here to here in a frame, then it's going to be a problem, even though that's the same speed as if you were going from like here
Excuse me.
to here in a frame.
Right. It's
So
like, where did you start from, and where do you end up based on the speed amount per frame?
like they limit his speed in the original game, but sometimes if you just luck out to be lined up on a certain pixel from one frame to the next, then you miss the ground and you don't stay attached.
Mm-hmm.
So this is actually a good time to point out that Sonic uses collision detection for two different purposes, which are easy to conflate, but can actually be thought of as completely separate needs of the engine. The first purpose is you don't want him to tunnel through the ground, right? Like if he's moving around, he needs to hit things. Um, and this is the kind of collision you would have if you were making a top-down game with no gravity, like an RPG or something where you move around. Like you want walls that block him. He needs to bump into stuff. But the second
Sure.
thing Sonic does that he needs collision algorithms for is he follows the ground that he's on, like a roller coaster on a track.
Right, and
And
that's essentially why that last example you were showing fails, right? Because he essentially runs out of track, and his rays don't touch anything, even though you would think they would, and they
yes,
fall.
like if in the bird's eye view of Sonic is following this track like a roller coaster,
Yes,
um, he should just follow it and have no problem. But from the game's perspective, it's saying the only way I can stay on the track is by doing collision detection, and the collision detection algorithm I'm using has these failure modes, and so Sonic doesn't always stay on the track.
and this is yeah, this is a good part. This is part that I took for my game, what you're about to describe. But go ahead.
So, um, there's a couple of different branches the conversation could take here, but I
I
think I will just back up and talk about raycasts since we already mentioned them.
Yeah, take it. Don't let me guide you. I'm sort of guessing the direction you're going. So
No problem. It's mostly just all the things I have swirling around in my mind. So if you
sure.
have, or I'm not going to go deep into the math. I'm not formally trained in math myself, so hopefully this will be easy to understand. But if you have a line, and the reason why it's kind of grayish on one end and dark on the other is because it's just a simple way for me to show that the line has a direction. Like this is its A point on the left here, and this is its B point over here. Um, and then you have another line. You can find the intersection point where the lines cross each other using a very simple mathematical algorithm. You just go on Google, look up line intersection. It's a pretty trivial thing that people do all the time.
And as
And
I
this,
said, most of the engines, if you're trying to adapt Sonic to an engine, have raycasts or some equivalent of
yes,
drawing lines for collisions.
Godot, Unity, I'm assuming modern Game Maker,
I
they'll
believe
have 2D
so.
raycasts even when they're not 3D engines, I think.
Yeah.
And so the function will be like, given this terrain line and this actor line, find the point of intersection. So if you, the nice thing about mathematical line intersection is it's continuous. If there were like it's projecting out mathematically like a ray of light and always finding the point where it touches. You're not sampling, oh, is it touching here? Oh, is it touching here? Oh, is it touching here? No, you just given the two lines, this is definitely where they cross.
Yep.
Now, obviously, there is the situation of parallel lines where they never cross, but that's not important. The answer is just that they never cross. So you can find if there is a collision between lines really easily. So if you imagine that you made a game where your environment was entirely made out of lines, like we're just going to have a big lumpy potato of terrain that the character wants to be able to run around on. It's a polygon, basically. And a polygon, it can be made, 2D polygon can be made out of a series of lines.
Sure.
So it would now be trivial to say where that terrain is when intersecting a ray. I always have a little bit of misgiving about saying ray because mathematically a ray has an origin and continues out forever. But for my purposes, it also has an end. But most game engines just call them rays.
Yeah.
So as you can see, I can draw all the lines I want in here. And this tiny little app that I made for the purposes of the stream is made in GameMaker 8, and it's finding these points just fine. Like, it's 15-year-old software, and it's having no problem finding the terrain, no problem. It's like one function, find the intersection point. So if you imagine you had a very tiny game character that didn't really have any size, like they were an ant, then they would crawl along the floor the way Sonic follows paths. They wouldn't have any size. They'd just basically follow the terrain as if it were a track. So if that character moved, they moved from point A to point B in some direction, like they start here and they wind up here. Because they don't have any size, their movement in that frame there is a line, right? Their origin point to point that they want to move to based on their speed, like this would be their speed vector. It's just drawing a line through space. So this ant, no matter how quickly it was moving, could be simulated as a raycast. You could say, hey, I'm here, I'm moving really fast. Maybe I'm tunneling all the way through this terrain, but it doesn't because the raycast finds the intersection point. The little ant guy would land on the terrain and be perfectly happy. So if you have a game about an ant running on potatoes, you're good. You use raycasts. Everything is hunky-dory. You can never tunnel. You can never have any ambiguities. And then once you're on the ground, it's just a matter of following the ground with moving forward in the direction of the in the vector of the ground. And there are many ways to do following a line path here, but that would be ideal. There's no collision system discretely sampling the ground and saying, is there ground here? Once you have intersected it from the air state, like you're falling, you intersect, now you're on the ground, you're in the ground state. Well, in the ground state, you just follow the path. You aren't having to do collision to say, is the path there? You just follow the path because it's defined. You know what this line is, you know how long it is. So if the player moves with speed, they can move in that direction with that speed, and then when they are past the end of the line, they just move on to the next line. And so does that make sense?
Yeah, I mean it's a simple follow the path, but that leads to
It's
the
basically unbreakable collision. You can never tunnel through anything, you can never miss anything, because it's 100% continuous from transferring from the air to the ground. It's always going to be flawless and accurate. There's no gaps or confusion going on.
Yep. I think that makes sense. Yeah.
I mean, I could
So
cover more of
like
the.
I mean, I was going to say that leads to the obvious question, like, why can't you just do that with Sonic? And I know the answer to this, but
Yes, that is definitely a good segue to the reason why it's hard to do that with Sonic, because Sonic is not an ant. That's another knowledge bomb for you. Sonic has a size, and so um, there is a concept in collision detection that is called the Minkowski sum or difference. They're related concepts, and got a fancy name after a scientist who worked on relativity theory and things that are way above my pay grade. But the point basically is that if you have a piece of terrain here, and you have an actor, and you want to know whether the actor is overlapping the terrain. Earlier I mentioned box to box overlapping being like checking the sides and stuff,
Hmm.
but there's another way to tell whether the actor is overlapping the terrain, which is to say expand the terrain by half the actor's size, and then just check if the center of the actor is inside that new box. And so I will demonstrate that in a way that might make more sense visually. If you imagine this actor sweeping around, aside from my jerky mouse movement, sweeping around the terrain in like an infinitely smooth mathematical way, such that it occupies all of the perimeter of the original shape. Like there's one here, there's one here, there's like it's just everywhere it could possibly be that's not inside or overlapping. Then what happens is the center of the actor, as it sort of smoothly rolls around the perimeter of the shape, is it's going to create a path through space that is kind of like this.
Hmm.
And I can show that by turning on rails here and turning snapping off. And so like if I move the actor around, you can see they sort of, I can't do it very precisely with the mouse, but they're basically drawing a square, that gray trail line around
You're
the terrain.
essentially drawing a shape or an extrude around the terrain that is half the size of the player in every direction.
Yes. And so if I turn on that visualization here, you can see the larger box around the terrain. So now if I put this actor anywhere, like if it's over here, its center point isn't in the larger box. If it's over here, its center point isn't in the larger box and it's not overlapping. But if I put it here, its center point is in the larger box and it's overlapping the terrain here. So this larger box basically becomes an area that you can test whether the center of the actor is in that area, and that becomes an equivalent test to seeing whether the actor is overlapping the terrain. It's sort of a relativity thing where you say, make the terrain bigger by the amount that you're making the actor smaller, and it's always the same answer to the question of whether it's overlapping because the distances are compensating for each other.
Sure.
So if a single point is inside this field, then an actor with that size would be overlapping the original piece. And I can show that with um, a circle as well. You can imagine the circle rolling around, tracing this out. And now, anytime the center is inside the bigger area, you know the two circles are overlapping. And so this expanded shape with expanded out by half the size of the actor, broadly speaking, uh, is called the Minkowski sum.
Mhm.
And you can sum any two shapes.
And
There are some nice live examples for like a disk and a polygon on Wolfram Alpha. Again, you can just Google it. There's lots of shorts on YouTube where people talk about Minkowski sum for collision detection. It's not that novel of a concept, but yeah, you were about to say?
I was just gonna say, so like if you were to adapt this for a Sonic engine, essentially all of your terrain would have this sort of extruded uh field area sort of, and anytime, and this is how Sonic becomes a single point in space, because anytime, because you can check that single point of space, the center of Sonic, and if he is inside of that area on any of the platforms, again, each one is generated, or each one has its own extrude, or sort of, I'm calling it a field. But it's essentially a collision field. And when he's inside that collision field, that's when you know you should land or potentially be on a wall.
Correct. So, like, you got it exactly, which helps me know that I'm not running my mouth here and I'm actually explaining it in a way that makes a certain amount of sense.
Sure.
So, I just showed that example with single boxes and single circles, but again, if you had any kind of shaped terrain here that you wanted Sonic to run on, like, it doesn't matter. And then you have, for example, this sphere or disk, I suppose I should call it a disk since we're in 2D, that represents Sonic. I have turned the extrusion on here, and so you can see that all of the lines that are normally this size have all been extruded outward by the radius of that circle. So the circle would, um, if it were inside this field, then it would be flush with the line.
And so that's how you turn Sonic into an ant. That's how you make him one line. You essentially have to extrude out the the um the terrains so that to account for Sonic's height. It's almost like, if you've had a record and you put a dot at the center of it and you put a dot at like the outside of it, the dot on the outside is going to move further than the dot on the inside, but they're both going to do like a 360. And
Yes, they move further in space, but they have the same angular speed.
yes.
Um, so like if I do a raycast here, it finds the intersection with the extruded line now instead of the original line, which is down here at the bottom. You see these little blue circles linking up the lines into a path. And then we've got the extruded line here. This is the intersection point. And so if I turn on the display, you can see that as this intersection point moves around, that circle that's the same size as the actor we're considering here, it's always lined up with the original lines which are in light gray here. Now, one thing you will notice immediately is that there's gaps in this path, and that's a problem. So, unlike with a single circle or rectangle, finding something akin to the Minkowski sum is a little bit more complicated because you have to have a way of closing those gaps. So, fortunately, it can be done in a lot of different ways, but I'm going to um, demonstrate a couple of them. Wrong type of object. So, to get these um, extruded lines, I suppose I should explain that first. You see these arrows, that's the perpendicular vector to the vector of the terrain lines that are drawn here. Like this is a line, and then this line would be perpendicular to it. So that's the direction, and the distance is the radius of the actor, which you can see that lines up here. So you're basically taking the line and you're saying move it out by the distance and in the direction that's perpendicular to the line. If this were like a 3D model, that would be uh, analogous to the face normal, I think.
Yep.
You've done more 3D
Yeah,
than me.
that's right. I almost said that's normal.
So there are two issues with doing it that way, because even though you get a good uh, shaded region like a rotated rectangle over the length of the line, where they meet, you have a gap if it is a convex bend, and you have an overlap anywhere that you have a concave bend. So one thing you can do is you can say, what if we, instead of using the face normal, used, I think this is called a vertex normal, where it's the average of the angles that are meeting here.
Sounds right. I don't know for sure, but it sounds right.
So like this piece has an angle, and this piece has an angle.
Mm-hmm.
And the difference between them divided by 2 is the average of those two angles, and it sort of sticks out at an intermediate angle. And for me, whenever I'm thinking about angles and trying to demonstrate them using like really obvious, familiar, simple angles, like here's a 90-degree angle here, then 90 divided by 2 is 45, so you go from a right angle to this diagonal angle. So whatever it is, it's always in between, and here's the other direction here. And so again, it's basically 45 degrees out in this direction, and you've always got an intermediate angle. So
But
now we
that's why
have,
you need to use the normal instead of the vector.
yeah, so now we still have, in terms of lines, one line per original line, where this is a line, this is a line, this is a line, this is a line. So it's like a one-to-one relationship. We haven't closed the gaps with new lines. There's still one line for every original line of the terrain.
Yeah,
And
and
so now
they're essentially slanted to meet, yeah, with the average. Okay.
that I've demonstrated that, it looks a little bit more um, reasonable when, let's just draw another potato so that the whole idea is here. You can see that it's extruded out this bigger potato shape that the actor can run along. But oh, we're having some trouble here, where now the actor is overlapping our original lines. Even see, it's overlapping here, even though it's following this new line. Well, the reason for that is, and it was really obvious when there were these right angles here, the shape gets distorted.
Right. And I guess I would say like this is all very theoretical, and you could implement this at least I guess I'll say theoretically in 3D by using or in with polygons either way, and the normal way a polygon would scale. So like if you wanted to manually do the extrude in Blender or something, or the normal way a scale works is through this vector scaling. But like Mercury is saying, we need essentially a normal scale. I'm not sure that's the right name for it, but um,
Yeah, I
it's a
don't
similar
know what it
concept.
would be called in a particular context, because I mostly re-derived this myself as I was just working on sonic physics. So
Sure.
I found out, because my Google foo was weak, so I just had to figure it out myself, that if I want this to be adjusted correctly, I'll change the mode here. It needs to look like that, so that the angle of the lines is preserved as well. Because when it's like this, these lines were straight up and down and straight left and right, but now they're slanted in order to reach that crimped middle piece. But by doing this adjustment, they're straight up and down, straight left and right, like all of the angles are preserved, and now the actor won't overlap the original lines as it follows the new lines. And so that adjustment can be done in two different ways. So it's a little bit of math here, but like if we go to our non-adjusted mode here, where it would be like this. You've got a distance here that it needs to be, like if you're considering this line with point A and point B, this line needs to be longer by this amount, and this line here on the right needs to be taller by this amount.
So you have to find the intersection by drawing the lines out further.
So if you know this angle between them, the average angle, like I said before, then these extensions are easy to calculate. If we say that A is the average of the two angles here, then it's the tan of that angle.
Oh, it's always the average of the two angles? Or,
yes.
Okay. Because like 90 plus 90 divided by 2, 90. Sorry, I just thinking. I didn't mean to interrupt you too much.
See, when it comes to programming, you might have some values already known from how the engine has already been coded, so you just can extend the line out by that distance, which is going to be the, I should say, the actor's radius times the tan of this angle here is going to be the distance.
You're losing me with some of these math terms, so like, I'm going to ask you.
They're just functions you're going to have, trig functions you're going to have in any programming language, like you have cosine.
I understand that, but
you don't have to understand them very well to use them.
No, I get that. What's confusing me here, and it's probably something silly, but that so like the line sticking out is 45 degrees.
Yes.
But that isn't the average of 90 plus 90 divided by 2. So where are you applying that 90 degrees?
One angle is 0 and the other angle is 90. So their sum is just 90.
I'm more.
And then 45 is.
I don't know what I was thinking. I was having a brain fart. Okay, of course. The flat angle is 0 and the straight up and down one is 90. Of course.
Yeah.
Okay, so then the division of them is 45. All right. I'm slow. Go continue.
Yeah, I have problems with angles all the time myself. So like this extra distance that you would want to add on to the line to get it to line up with where we want it to be, like that.
You would project out that 45.
Yeah. Is the radius times the tan of the A is like the average of the angle between them.
Sure.
So the second way
that's all I had. Sorry.
Is to say that this line here, this sort of vertex normal, could just be extended outward by the amount that we need. Like if this length here were out here, right? Like you already know this angle if you could just stretch it out. So it just depends on what you want to calculate in order to find your new end points. If you're like project outward from the vertexes by a certain distance or extend the ends of the line by a certain distance.
Yep.
So the algorithm for that is going to be the radius divided by cosine of this angle. We'll extend this short blue length to this long orange length, and you're going to get the same point. So that is how you do expansion. Now, this is similar to the Minkowski sum, which I brought up so that you've got a term you can Google if you want to go into further reading and stuff. But technically what this is doing when I make these shapes, I do not think is strictly a Minkowski sum, because the way that's defined is that the new shape has to contain all of the same points of, as if this were moved all the way around it, right? But here I'm only using the one axis, the y radius of the actor, particularly for when I do it with a rectangle. So like everything I've talked about with how to extrude these points is the same. I'm just saying, like, don't think of that as literally a Minkowski sum, because what it ultimately winds up acting like, and I guess I should do that. I guess I should do this with a right angle again, because it's probably the most demonstrative, where yes, I want to draw my line here. It's done in such a way, when you extend it out in this way, the way it works is it's always the right shape for the actor if they were rotated to line up with the terrain angle, which I can demonstrate better by having a more exaggerated difference between the two axes. See, like a Minkowski sum for a rectangle with an actor of this size would be like thin on the sides and thick on the top and bottom, right?
Sure. So you're saying
But
the
this,
shape wouldn't rotate with the axis of the, or sorry, the player wouldn't rotate with the axis of the
of the
terrain.
terrain, yeah.
Yes.
So obviously you want Sonic's distance from his head to his feet to be the same as he's running around the ground. So it makes sense to do this extrusion in such a way that it is appropriate for rotating, as opposed to just sliding with no rotation. So I just say that because I don't want to be spewing misinformation and be like, oh, I've generated a Minkowski sum here. It's like, no, I'm just doing something conceptually similar, uh, but
Fair.
specifically for rotating a character around. So if you were to draw like something a little more circular, a little finicky to draw here, keep picking up the old pieces, then anytime you draw a ray intersecting, it's going to line up just fine with the rotation in order to follow that path and rotate the character around it. Like if they hit from this angle, then it'll be like that. So that would be how you'd land on curves and stuff from the air, because the little point hits the extruded path, and you've got the right rotation and you can follow around. So in order to make this less abstract, we can have a little bit of fun here and look at this actually in action here. I've got a
dot
little
engine, movement
test
engine.
engine here. Drop the player, zoom in a bit. I don't know. Can everybody see that okay?
I think it
We've
looks
got
great.
a circular actor, and they're running on some terrain lines. They follow the ground. They fall off of ledges. They follow the ground. There's something. You go launching into the air like a ramp. You have some kind of a loop shape here. I can fly through the air with infinite double jumps just for demonstration purposes. And so what's happening in this engine is it's implementing what I've just talked about, but it is calculating those extruded lines on the fly, and here they're shown. Any of the terrain lines here that I'm highlighting that are near enough to the player generate their extruded version, which is what the player is actually colliding with. So as far as the game is concerned, the player is just a single point, and you can see as I move around, there's that line drawn to the center of the player in the middle of the circle, the white line. That's basically the raycast, the single raycast that's being done along their movement vector to say, oh, have they hit the ground or not? And then they follow the path, and it works great.
It
And
almost looks
because,
backwards, though. Why does it look backwards?
probably because I was zoomed in and there's not anything to gauge the relative motion by.
Okay.
Oh, the white line looks
Yeah.
backward? It's being drawn from the previous position to the current one.
Oh,
So
okay.
you're seeing the frame after the player's moved. So yes, it would actually be in the opposite direction of their movement.
Okay.
Um, so one nice thing about this engine is, unlike Sonic, it's never going to break no matter how fast the speed is. Like, you can go around these ridiculously tiny things. Of course, I do have the fall check for when you're too slow on a wall.
Mhm.
He's not like SBO where he can just run on a wall forever. So that's why I fell off there. It's not because he didn't find the ground. It's because he was too slow and decided to fall like that. But as long as you keep up the speed, it's a little hard to hit this with enough speed. This is why I have the system for launch the player following a particular angle. Yes. So it's very
That's great.
dizzying, but like if this were one of those things in Scrap Brain
Scrap.
Zone that you run
Yeah.
around and were that tiny, Sonic would just fall off of it and have problems. And the same thing is true for.
Yes, his rays are basically bigger than, or at least as big as that circle he drew there. So
Yeah, it also works for concave. If I can land inside this little wrapped thing here, I really should have turned off the fall check because I'm not getting enough speed, but I can shoot into it like that. So yeah, like, it looks crazy, but the point
it's
is that
getting
this
there though.
ball is rolling
Spinning around
around
in there really, really fast.
this little bit of terrain, and it's not flying out, it's not getting trapped, it's just perfectly,
Yeah, it works great.
essentially flawless.
Can you turn on the? Oh, okay.
What were you gonna say?
No, it was fine. You don't have to go back. I was gonna say turn on the calculated line again while you were in there.
And of course, here's an imported
Emerald Hill
existing
Zone.
Sonic map. This is This is based on Emerald Hill. So you're going to have all the same kinds of things. Now, there are differences in this engine from a real Sonic engine. I'm doing some like trigonometry for calculating the speed he lands back at a slope with. It's more of like a digital either or in the real game. Those are just like aesthetic choices, not limitations of the engine. So this,
You're talking about landing speed? Or...
right, like he's going to lose a little bit of speed if he's moving toward a slope when he hits it. I'm just pointing it out because I don't want someone to look at this and go, oh, that doesn't look like it's moving with sonic physics, because it's technically not. It's just demonstrating the collision.
Gotcha.
Because Sonic would have like more of 4 modes kind of decisions about what speed to preserve or not, as opposed to being smooth based on the angle that he collides with.
Gotcha.
So that is the central idea, to sort of collapse everything into just a point moving through space, doing a single raycast, which makes it continuous. That doesn't cover everything because there are a lot of little things that you need to do, because there's this tension between realism of having, oh, now the physics are smooth and they work flawlessly, and emulating the quirks of classic Sonic that you actually want versus the ones that you don't.
Yeah, like ramping around corners on loops and such like that.
Yeah, so there's a couple of other things we could cover if you are still up for it. Were there any questions in chat or anything to get to before I drone on for longer?
No, you can go ahead.
All
I
right.
guess I'll just say, hey Jaden, thanks for showing up, Jaden Pixels. Dream stops never. I am working on Time Twist and No More Robots. They I'm actually going using some of the concepts Mercury's talking about for No More Robots. So yeah, but other than that, you can go ahead and continue.
All right. So one thing that is important to note when handling collision like this is the movement of the actor. Let's say you're in the air state, and this is your movement vector, and it intersects the ground here. And this isn't extruded because it's just a simple example.
Sure. Oh
You
no.
want to know how.
I'll be 1 second.
I think Overbound had to leave for a second, but I am now trying to talk about. Well, actually, I won't start with this as an example. I'll
I'm
talk
back, by
about.
the way. I had a battery issue with my laptop.
Got to plug in the old charging cable.
Yes.
So if you have, I'll use these boxes just because they're a little bit more visible, but you can imagine it's outlined terrain.
Mm.
So if you are thinking of classic Sonic and he's able to jump toward a wall, and like if he's in the upward arc of his jump, he'll hit the wall, but he'll still continue up until gravity starts pulling him down. Or you could be falling toward a wall and you'll smoothly slide along it until you land. So what's happening here is there's going to be some movement toward the wall and some movement in the y-axis, either up or down, but we can pick one just for the example and say you're falling. So you've got a wall and you've got an actor and they're falling along the wall. Well, that means that their movement vector, if the player isn't pushing any directions on the controller, and if there's no um, momentum hanging around for anywhere, that movement direction vector is just straight down. You imagine it's only gravity and it's increasing, and so okay, the player wants to move down, and they're flush with the wall, so there's no problems.
Okay.
But if the player is pushing on the controller to the right, they're going to be accelerating the actor a little bit. And so the vector won't be perfectly straight down. It'll be like down with just a little bit of motion to the right, just like a little bit of a diagonal.
Okay.
And so now if you imagine that I guess I don't have to say that you imagine it, I can turn this on. Now you've got the extruded path that they're colliding with. So we just move this out of the way so it's more visible. You've now got this ray cast starting on the boundary of the shape and penetrating into it. So if you always set the actor to the intersection point when there's a collision, then the player needs to move down so that they can fall and slide along the wall as gravity is telling them to do. But their movement in the horizontal axis needs to be curtailed because the wall is stopping them. But this intersection point is like right here at the origin of the ray, so no movement is going to happen. So the circumstance would be that the player would jump into the wall and they'd hold toward the wall, and then the player would just, character the player is controlling would just stick to the wall and hang there until they let go of left and right, and the horizontal part of the vector went away and there was only a vertical component left, and then they'd be able to freely slide down the wall, which obviously isn't what we want. So the principle here is that when you have a terrain and you have the actor's ray intersects the terrain, you actually want them to keep going by a certain amount. So in the wall example, where the intersection is happening right here at the start, you don't want any horizontal motion. You want to move, I'll do it here. You want to move straight down the amount that you would have moved down if you weren't pushing to the right. So what's basically happening is anytime there's an intersection, you have some amount of movement that you didn't get to do because it was blocked by the terrain. And so now you need to trace along the terrain by some amount that is equivalent to the amount that you didn't get to move. And I have struggled with explaining this in a way that makes sense, but like if you were moving around in the air and there was no terrain and you wanted to move, let's say your speed was 10 in some direction, like 10 units in some direction, then there's nothing to stop you, so you move those 10 units and you're fine. But if you are stopped by terrain, you didn't get to move 10 units, even though that was the speed the character was moving. That's the impulse they had. So you're going to lose a little bit of speed when you hit the terrain. For example, probably the trivial example of this would be the floor and falling straight down. You're you're going to want to stop completely because you don't want to fall straight down and then scoot along the floor like it's ice. You just want to stop.
So I
But if you
apologize if I'm making you repeat yourself here, but
no problem.
can you remind me of the behavior in the classic Sonic games? Because
Yes, his speed is preserved when he hits a slope, right? It'll say, "Oh, I hit the slope. How much should I
but
have
it
speed?" It'll be the same speed. However, he doesn't actually move in that frame.
right, okay. And
which isn't a problem in the classic engine because it separates horizontal and vertical movement. So if it blocks his horizontal movement, it'll still then, in a separate step, move him vertically. This is not exactly true in the air because it does a couple of different things, but on the ground, it'll work that way. But when you're combining horizontal and vertical movement into a single vector in a direction like I do in this demonstration, then you have to keep moving in the amount that's left over. Otherwise, you'll just get stuck.
what you're saying when you say the amount left over is you're talking about the vertical movement that should still happen while the horizontal movement should be canceled.
Correct.
Okay.
So falling straight down onto the ground, there is nothing left over.
Right.
And you can think of that as a perpendicular intersection.
Mm-hmm.
So in that case, there's nothing, and you would cut the motion to just that distance. This amount that's left over wouldn't be used because you're stopped, basically. But if you're moving at an angle, you'd want to hit the ground and slide a little bit. So we can imagine that you've got an angle like that. You don't want to stop there. You want to keep going by some amount so
Mm-hmm.
that you hit and then slide a little bit, if that makes sense.
It,
So the question is, how far do you want to slide after hitting the intersection point?
right.
And Sonic would compare the angle to a certain threshold and say if it's higher than 45 or something, it's on the physics guide, then don't have any horizontal speed carried over, but if it's lower, then just use your entire horizontal speed and don't curtail at all. But if you wanted to do it in a mathematical way that was angle independent, you would do what's called projecting the vector onto the vector of the terrain. The movement vector would be projected onto the terrain. And what that basically means, in the way that makes the most sense to me, is you can think of it like casting a shadow. So like if this is the orange movement vector and this is the terrain, you think of it as a stick standing up with a light coming directly from above, it would be the shadow on this line would be roughly like, well, it's hard because I don't want to draw it over the other line, but like it's going to be basically that long, right? That's the shadow that this part is casting onto here. So you've done this movement, then you've hit the ground, and now you've got this amount left over that you want to keep doing. So this is the part that you project. And so you wind up turning this vector here into one vector and then another that follows along the ground with the trailing speed. So I
Okay.
don't necessarily
And
want to get bogged into the math details of that, but it's important that in the same frame, that leftover speed is taken care of. Otherwise, you're supposed to be moving diagonally and you hit something, you're just going to be stopped like it's made out of glue rather than sliding along it the way you would in a classic game. That's one of the pitfalls of doing it in like completely 360 engine where the axes aren't separated. You're moving diagonally in a given step. You have to complete the movement even if it's interrupted, if that makes any sense. Yes?
um
You were going to say something?
I lost my train of thought, honestly.
Okay, sorry.
No worries.
Now, there is another thing to consider, which is that when you are following the path on the ground, you have to think of it as still moving through space. And if for whatever reason, because Sonic games can have, moving platforms, other chunks of terrain, crossing paths, multiple objects next to each other that aren't made out of the same path, you could have a situation where a piece of terrain is crossing another piece of terrain. And if you were just blindly following the ground here, you'd pass right through this crossing piece as you were following this.
Mm-hmm.
Now, I can imagine there are games where pieces of terrain never overlap each other and everything could just be a path and you'd be good. But all this ultimately means to cover this situation where you would hit this, like trying to think what a good example would be. Actually, this is a pretty good simple example. You've got a floor, right? And you've got another floor because you can like jump and land on here and jump and land on here, like in Green Hill where there's hills and you can
Through
jump onto
floors you're
multiple
talking
layers
about.
of the level, right?
Yeah.
But then there's also some other structure that's just like a wall that's crossing both of those.
Right.
You wouldn't want to have to, as the level designer, be like, okay, make sure to split this up into a bunch of weird chunks. Like this wall is going to be crossing those other lines. So if you follow this line, maybe I should turn the extrusion on. If you follow this line without checking for intersections with bits of terrain that cross the path you're on, you're going to miss them out.
Right.
So the solution is really simple. When you're following the ground, you just raycast along the ground the same way you would if you were moving through the air. And if you hit something that's not on the same path as you treat it almost the exact same way you would if you're on the air, in the air, I should say, where if the angle is too steep, then you bump into it like a wall. And if it's shallow enough, then you can transfer and run along it on the ground. So even once you're on the ground following the path and totally locked in, you still need to check for collisions with anything that isn't the path you're following, assuming you want overlapping paths in your game, which admittedly, not all games are going to have that complex of geometry.
Sure.
So that's another thing to keep in mind.
Tracing a raycast on the ground to look for other terrain that aren't part of your current terrain.
Yeah, because you never know when some moving platform has showed up and you're gonna need to deal with it.
Sure.
And yeah, it's probably easy. Well, I'll show it in here. Let's make something a little bit like curve out of multiple pieces here. A little wobbly, but you can probably
Half
see
pipe,
it,
quarter pipe, I mean.
that you've got this curve you need to follow.
Mm-hmm.
So if your movement was saying, let's pretend, especially since I was showing it in the live example, that your movement vector is like really, really fast. You're going super fast. And this is the amount of speed that the character wants to take. They want to blow right through this wall, but of course there's a bend in it. So they should wind up, rotating and running along the wall instead of this. But as you
Right.
can see here, the first intersection they're going to find, I suppose I should put the player here, so it lines up with the whole thing I've been talking about this whole time with the extensions. Extruded path, like this is what it would look like to the player, but we sort of turn debug mode on and see the extruded path that the center of the player is following. So
Mm-hmm.
if their movement vector is like, hey, I want to go here, Well, this little, they're going to hit this first um, change in angle here.
Right.
They're going to intersect that. And then because you're running along the ground and you don't lose speed in Sonic when you transfer from one angle to another, it's not like he's colliding and encountering some kind of friction. There is the slope factor, but that's calculated separately. Um, Basically, you just want to follow this path with the amount of speed that you had. So you would conceptualize that as saying, okay, now we've got this new vector we need to follow along. And now that's intersecting the beginning of the very next change in angle, and then you need this new vector, and then you need this
So is what you're
new
getting at that
vector.
this isn't a true curve?
Yes.
You're traveling along straight lines that are, sort of approximating a curve as polygons do.
Yes. So a naive implementation would just say go until you hit something, and then carry over what's ever left over from your speed. But of course, if you have a bunch of little segments in a row close together, your speed might be enough that you encounter. It's never going to be that many under normal circumstances, but like a handful of intersections in a row. So it works best to have a recursive algorithm that keeps moving with the leftover speed until it runs out, no matter how many intersections it encounters. So that at the end of this frame, like this would all happen in a single frame because you're going like ridiculous, stupid fast. You'd go from here all the way to like way over here. Oh boy, turning that on is not helpful. Um, and like all of this motion would have been taken care of in the one step because the algorithm that resolves the collision is recursive and says, okay, you hit something, now keep going. Okay, you hit something else, now keep going. And that would all happen in one frame before the graphics were drawn again. And this is something that is true in Godot, which you're using. It has like a move and slide collision system for its built-in bounding box stuff with like
Right.
actor capsules and however they implement it. And there's like a resolution that you can set for how many times you want it to try to resolve a collision before giving up. Um,
Hmm.
so like for the most part, you're not going to notice as a player if you just do, cap it at 3 or something. Maybe there's a couple frames in which you don't move as far as you would have expected, but it's only ever going to be occurring when the player's moving so fast they're crossing multiple segments in a single frame. And so that's one way that you can be confident it's not going to get like trapped in an infinite loop or something like that, and reduce the amount of work that happens in a single frame. But you do have to resolve multiple intersections because otherwise it'll feel like anytime you go around a curve that's made out of multiple sections, it'll feel a little bit jerky, like you're stopping against each one, like each node where they intersect is like tripping up the player. Uh, if you want the motion to feel smooth, the amount of speed needs to be carried through the path, which means tracing every one of the lines. Now you could trace a truly curved path rather than breaking up into line segments. It just involves having extra math for checking for intersections with curves, which is something that I can cover in the future as I um, have better tools for demonstrating it and working it out and implementing it in the engine myself. But for the moment, line segments are sufficient. Um, as you could see with the live example, they look just fine if you have enough of them. So
So
again, it's
uh,
just
I
another thing
think
you have to
I
address when
think
you do it
I'm
this way.
I think I'm missing a little bit here. With this is essentially required because of using vector math instead of um, a set of points. Is that accurate to say?
It is a consequence of the vector math, yes, because if this were a discrete system like the classics, then if Sonic moved from here to here in one frame, then he'd just be like, it's hard with this example on because, right, like you're flush with this ground and then you suddenly move here. Well, then the sensors would push him out of the floor until he was here, right? Because he's just here on the flat ground, and he's over here on the curve, and so he's pushed out of the curve.
I guess.
But in this engine, you're tracing the curve, so the because it's continuous, the entire curve is encountered by the raycast. You can't skip any of it. So the first intersection is going to be here, and then here, and then here, right? Like here, and like I drew before. You don't get to just skip it up and then move to the new height that you found. You have to trace along the path without any gaps.
I and what effect does that have on speed? I think I'm missing something, part of this or something.
If you didn't carry the speed through each segment, if you didn't say, okay, I wanted to move from here, like I was showing with the very long speed vector, you would expect this vector to sort of be curled up until it was pointing this way. Like the
Okay,
path the player takes through
and
space
you're
has to be
saying
curled up.
so like so what you're saying is I so we move this first vector and you encounter that line, okay, or the intersection point where it changes angle.
Yes.
At that point, you recalculate the vector and lose a little speed, and then you do it, and then you're on the new angle, which I'm just guessing here looks like about 5, 10, 15 degrees or something.
Yeah.
Um, and 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 again you're going to reach the end of that angle where it slopes again, and you're saying, and at that point it's going to recalculate again. And so is your point that you're losing a little speed each time and it's not that accurate? Is that, or am I missing something? Because I
Well,
understand your
you
concept.
don't actually have to lose speed. You just have to change. Like if you didn't keep going, like see this dot that my cursor is on right here.
Mm-hmm.
Um, if you just stopped there, then the player expected to be moving this fast. So if they're tracing the path, they need to trace the path this entire distance. But that distance would be curled up into an upward path. But if you just stopped at the first intersection, this entire distance here would never be traveled, right? This needs to be translated, this extra length here,
You're saying you
beyond
need to
the first
translate that
intersection.
each time at each intersection.
Yeah, so that the speed is carried around the path instead of straight through space. And if you don't carry that through every single bend, then it's truncated at some point and the player is not moving through the path at the ground speed's intent. It would be shortened somehow. So you have to recursively, every time you hit an intersection, say, how much was I supposed to travel, and then travel in that distance along the new line that you found
and
in
and
order to keep.
and your engine now doesn't support this, is that correct?
It does.
It does.
That's why he was able to go around the loops and everything in the example I was playing earlier with the in Godot.
Okay.
It just it doesn't do it does it through segments rather than doing
No, that's what I was asking.
circular math.
That's what I
But it
was
does
trying to
do
get
it.
at, whether you did the circular math or the segments. You're saying right now it does. I believe you said this earlier. Right now it
Yeah,
does the segments, and eventually you want it to get it to do the curves. Okay. But so
right, because
like,
that just reduces the amount of objects in the world, and obviously if it's a curve, then it has flawless resolution rather than having to decide how many pieces to make it out of.
But so right now, are you doing that recursive function, or are you just losing the speed more or less?
It's recursive. That's
Okay.
it's kind of inside baseball, but that's why it was a state machine that kept running until it was out of states.
Okay.
Um, so
All right. I
yeah,
apologize, but that makes it clear.
no worries. Um, so obviously I'm talking about this in the abstract because you can implement it in any programming language. You can ask an AI to do it.
Sure.
So I'm basically just covering the concepts.
Yeah,
Um,
this would be great for a transcript for an AI.
so they are. It's not as easy as saying, oh, don't use these sensors from the physics guide. Just use a raycast, right? Because once you're tracing it in a certain way and it is continuous, there's those pitfalls that require it to sort of recursively trace. Um, but if you handle that, like all that live example was doing is just what I've said here, pretty much. Like that's the entirety of how it's coded. Is you just land on the ground when you hit an intersection point, you carry the speed over from the projected vector, and then you trace the path. And then when you hit the jump button, you jump away from the path. Like there's not four separate modes. There's not a bunch of sensors that have to be rotated around. It takes 360-degree run around the terrain sonic physics and turns it into a very simple uh, raycast forward uh, concept.
Yeah, it's a great engine. It's very smooth.
Another thing you were mentioning earlier, like you could make these extruded paths beforehand. Like your level design could just be the fat path that Sonic runs on,
Hmm.
um, since it's invisible collision geometry anyway.
Yeah, and there's
But
probably a way to get Godot to do that extrude. I haven't looked at it, but I would imagine it has a function to do some kind of extrude by the length of the normal of a model.
but then
So,
my example I was showing you was calculating the extruded path based on just the nearby segments on the fly. And the reason why I do that, even though it would obviously be a lot simpler to pre-bake it, is that there might be multiple actors in the environment, Sonic, enemies. Sonic can roll up and he changes size. Tails has a different physical mask, collision mask size. So as you can see here, if I switch between different actors, like here's the small one, here's the medium one, here's the large one, it's helpful to be able to calculate the extruded path on the fly rather than um, pre-baking it into the level geometry. But again, it depends on the kind of game you're making. If you're making a game like Marble Madness or something where there's just a marble and it's always the same size, then you don't have to worry about calculating the extruded path on the fly. You can pre-make it, and that's just your collision geometry that you're working with. So that's another point to consider.
definitely.
So I think that covers everything. That is the crux of, hey, here's the big idea. Anything else would be answering questions or whatever we might want to save some of the more advanced things like corner tags and stuff for another stream, or are you still willing to go?
That is up to you. If you want to continue with the corner tag discussion, I'm down for that. I will have to stop here, perhaps like within the next 30 minutes to deal with my dogs, but I have at least that long. Or we can
Okay,
do part two.
then
It's up to you. Go ahead if you want.
yeah, and then talking about corners would be a good thing to end on.
Okay, cool.
So I will switch back to the Godot engine here to demonstrate that when you are actually, I've got this setting here that lets me keep pushing the wrong button. That lets me this bright cyan path here is the extruded path so that you can see the actor following it
Sure.
from its center. And as you can see here, it's a little bit of difference between what I talked about where this corner, when you're zoomed out, it looks like this is just a 90-degree corner, but it's beveled off here.
Okay.
Whereas the extrusion I was doing in the other example, there was always a one-to-one relationship between the original line and the extruded line. And there still is because there's this little bevel here that when it extrudes is being magnified into this bigger bevel.
Okay.
But this actually isn't part of the level data, this tiny bevel here. When it loads the line segments that comprise the level, it just says, hey, if there's a 90-degree bend, then I know that's not curved ground that Sonic needs to run over because he doesn't run around 90-degree bends in the real game. He runs around curves, right? So the engine just, when loading the level data, for simplicity's sake, although you could do this any number of ways, it'll just automatically bevel off those with a little 45-degree segment, and it tags it as, hey, I'm a corner segment.
Mm-hmm.
And the consequence of that is that now the terrain that the player runs on here, the player is going to be seeing this little segment, and unlike a real slanted segment that the player can run on and still be in the ground state, anytime you transfer to a segment that's flagged as a corner, you enter the air state. So you can imagine, like, if this were Sonic and not a circle, he'd be like in his balancing animation, right? Hanging on the very edge of the platform. And then if you tipped a little bit further, he would be pushed out and fall down past the wall. So this is the way that you get that sort of corner bumping that you get in classic games, where you don't just stand really far out on corners, but if you jump down or up past a corner, you'll get this like bump effect.
Where it sort of bumps you out of the corner and so you slide
Yeah,
down to
makes
the
it
wall.
more natural, especially because your actor is usually capsule or circle shaped in a way that it would look weird if they treated the corner as this edge that you get caught on. So it's just a little bit of grace that pops you out.
Would it be
And
fair to say that this is like, let's say I had a half pipe right above this, facing from the ceiling to the
gosh, sorry, my
trying to make
keyboard
one,
wasn't working.
but top left half pipe there, right? Top left corner of your loop, or most of a loop.
Right,
Um,
like if this were closer to here.
well, I, sorry, I said top left. I meant top right directions. I'm talking about the top left quarter pipe. Or sorry, I'm still saying left. Brain's going. The top right quarter pipe.
Uh-huh.
If you had that like right at the edge of that 90-degree angle, um, in a classic Sonic game, you expect that you'll just fall down the wall, right? Like you don't expect to get like hitched onto that tiny bit of ledge. Are you following me? No.
Not exactly.
Okay. Go back where you
Tiny
were.
bit of ledge where?
Well, go back to your other example. Run back over to your 90-degree angle, just so. No.
Sorry.
No, you're good. So
Maybe I
if
can
think about
maybe I
okay,
can use
let me
Emerald
just
Hill there.
actually think about a J, okay? Like an upside down J, right? You've got a curve, the ceiling's curved, and then you run down a wall, right? An upside down J.
Right.
So like a loop without a bottom curve, or more or less. Um, and then inside, and then on the right wall of that J, there's a gap. So like it's chopped in half, right? Like so
Like if this wasn't here.
yes, exactly. If that wasn't there and that bottom curve was straight instead of curved, if it was just a wall, so you would like run down the wall, but it had a hole in the wall, then you would just continue to fall. You wouldn't like snag on that edge of that. At this point, it would be a platform because if there's a gap, it's a platform. It's no longer a wall, right? I mean,
So you're saying the corner piece sort of acts like an on-ramp to reacquiring the ground.
I'm asking if that's the case, and I'm I'm asking how the classics do because I don't remember exactly. But if I recall correctly, like if there's a gap in the wall and you have like uh a loop, or if you have like a four sided loop, like let's just say Sonic's in an oval, right? There are walls and there's a gap in one of the walls. You can still run around the oval. You just kind of skip over the gap, right?
Right.
Hopefully, I'm making sense. But uh, in your
You
case,
are like in I think Green Forest in Sonic Adventure 2 and also in Leaf Forest in Sonic Advance 2, aren't there loops that are like missing part of the top?
yeah, like those tree, they're like tree trunks or something.
Yeah.
Yeah. So this would be more like the side, but the
Right, the
concept is
same
the same.
principle but the side's missing, yeah.
Yeah, and so I'm just asking though, like fall down, when you fall down a wall and you hit a gap, and then there's a floor, but the wall continues. Like, are you? Yeah, maybe draw it out.
Yeah. So you've got some kind of loop and then it has a break and then it
Yeah, the bottom
uh,
loop isn't as important. It could be a wall for all it matters.
let's
But
make this a little bit.
the top needs to be the curve. Yeah. So that's a curve, and you're running down that curve to
Or up,
the
I suppose, either way,
yeah,
up or down.
but but down's going to have gravity. Um
Yes.
so you're traveling down and you hit that little bit of an edge there, but you don't actually hit the little bit of edge. You just smoothly go down the curve, right?
Right.
And so I I'm I'm trying to understand, like, with what you're doing, is this behavior going to be the same? Like,
Yes, because my understanding of the classics is that he can't land on a wall at all. So it's like if you are traveling along here and then like he's still grounded here, he's running on the top.
right,
And then the minute there's nothing, he's in a falling state.
right,
And then he's not going to land on this wall. He'll still be in a falling state until he hits a slope.
right,
Ground has to be at least slightly sloped in Classic Sonic for it to say, oh, time to land on the ground.
right. But
So the
I
same thing would be true in the reverse. He would just be going up here and straight in the air until he hit the slope.
sure,
Now, if you were, for example, running off of this as a ramp and you were pressing to the right, he would ever so slightly edge into this gap, and then he would hit either the ceiling or the wall with one of the sensors and have to decide what to do. And
right.
pretty sure he would just be pushed out of the wall and keep going up in the air state until he hit a slope.
Yeah, and so I'm wondering how this like okay, so you said yours functions the same way.
Yeah, the corner bevels would have the same result,
Okay.
but you could code them not to do that. Like you could flag a corner bevel as an on ramp to a loop that you wanted to be able to take like that if you had a gap in a loop.
Yeah.
Um, the kind of nice thing about having the separate segments is they can have metadata that can give you special effects.
Yeah, that is nice. Okay. Thank you.
So, yeah, that's basically the idea. You don't have to have a one-to-one relationship between the original terrain and the extruded terrain. You can bevel off the corners for um, certain effects like this, where it's not really ground that you can land on, because in the air, if you hit it, you don't enter the ground state either, you just keep falling.
Hmm.
But it physically pushes the character out so that they never penetrate the ground and wind up in a position they shouldn't be. But it's not like you can jump onto, I mean, it's orange in this case. It's not like you can jump onto this orange um,
Yeah.
sloped piece here and then jump off of it. It still acts like in the classics where it's just a way to push the player out of the corner when they're close to it without landing on the ground. So, um, yeah, I guess that is the other thing I wanted to cover from my notes was the corner pieces. So I think we're pretty good to wrap up here if
Cool.
that works for everybody.
Yeah. That's great. Really appreciate you being here today. I
Yeah,
think
it's
you
my pleasure.
yeah. I really enjoy talking about this stuff, and it's really good for my understanding too. Um if people want to reach out to you, I think you said they could on Discord.
Yes, I'm Mercury Silver on Discord. It's all one word, all lowercase.
Okay. I can't remember. Are you in my Bound to Game Dev chat? I think you are.
I am.
So you can also look him up there as well. Yeah. I'm around too, and you can ask questions in the video comments as well. If you ask anything in the comments, I won't promise you Mercury's going to look at it, but I will, and I will make sure they get your questions. So I think that's it for today. Thank you again, Mercury. Really appreciate you being here, and I hope you all get a lot of use out of this. This is a great conversation. All
Yeah,
right.
thanks for having me on the stream.
Yeah.
It
All
was a
right.
good time.
Yep.